Alrighty, so in this video we're going to try to finish up our magnetism unit, and before we get to that, I want to take a look at a quick warm-up question. Okay, and so this is the warm-up question we would normally be doing in class, okay, but I want you to try to answer it on your own. So the question says, a charged particle moves through a region of space at constant speed without deflecting. From this, one can conclude that in this region, there's 5 different answer choices. I want you to read the question carefully, read the answer choices carefully, and see if you can figure this question out. Okay, so the correct answer to the question is E. And this is actually taken from an AP exam over 10 years ago, but it's a really good conceptual question. Okay, so let's take these answer choices one at a time. A says there must be no magnetic field. Now, that's not necessarily true. An object moving at a constant speed in a straight line has a net force of 0 on it. That doesn't necessarily mean that there's no force on the charged particle. It also doesn't necessarily mean that there's no magnetic field, because a charged particle could be moving parallel to the magnetic field, and if a particle moves parallel to a magnetic field, then there's no magnetic force. We've talked about that before, because there's a sine theta in the force equation. Okay, so A is out. B is out. There must be no magnetic field and no electric field. Now, it is true that if there was no magnetic field and no electric field, then this situation could definitely happen. Okay, but just because we see it happening doesn't necessarily mean that that is the only possibility. And so A is not, or B is not the correct answer, not because it's not true. It is true that is a possible situation, but it doesn't have to be like that. Okay, C says there could be electric and magnetic fields oriented in the same direction. And so just to remind you really quickly how electric fields work, on a positive charge, the electric force on a positively charged particle is going to be parallel to the electric field in the same direction as the electric field. That's how the electric field direction is defined. It's defined as the direction a positive charge would feel a force. The magnetic field is completely different, and the direction of the magnetic force is actually given by the right-hand rule. So if you had an E field and a B field going in the same direction, those two forces would not be in the same direction. Okay, and so C is out, because you actually want the forces going in opposite directions so that the net force on the particle is 0. Now, D, you might think would be the correct answer, because it says the fields are oriented in opposite directions, but just because the fields are in opposite directions does not mean that the forces are. Okay, because remember, the magnetic force, the direction is given by the right-hand rule, and it's in a completely different direction than the magnetic field. It's perpendicular to the field, as a matter of fact. And so just because the fields are pointing in opposite directions does not mean that the forces are. Okay, so the answer is actually E. If you want the forces acting in opposite directions to each other, then you actually need the electric and magnetic fields at a 90-degree angle to each other. And if you look at the picture down here and the explanation they provide, hopefully that also helps make more sense. Okay, so let's move on in our discussion of magnetism, and we're going to talk about the magnetic fields created by wires, specifically a wire that has a current running through it. At the beginning of this unit, we talked about how it is a moving charge that gives rise to magnetism. And so if you have a wire with current through it, we talked about current in the last video, that wire is going to create its own magnetic field surrounding the wire. And this was actually discovered kind of by accident in the 1820s. This dude, Oersted, was doing a lecture in front of a bunch of people, and he was doing an experiment with electricity, and he turned on the circuit, and there was a lot of current going through a wire, and he just happened to notice that as he did that, there was a compass needle nearby, and that compass needle actually reacted when he turned on the electric current. And so that was the first time we made the connection between electricity and magnetism. And upon further investigation, it was actually shown that if you take a compass and you move it around a wire, a straight wire, that the compass needle actually seems to kind of like trace out the path of a circle. And so this is the first connection we made between electricity and magnetism in the early 1820s. Okay, so what Oersted basically found was that if you have current running through a wire, it creates a magnetic field. The shape of the magnetic field can be found using a compass needle, you can just move a compass around. The compass needle is always going to line up with the magnetic field, and so if you are just really diligent in moving your compass around the wire, you can make some discoveries. I will also link a video where you can see this demonstration done with iron filings, just so you can visually see the shape of the magnetic field created around a straight wire with current. And the shape of that wire is actually a circle. Okay, and so it's been discovered through different experiments, like I talked about on the last slide, that if you figure out the shape of the magnetic field around a long, straight, current-carrying wire, the shapes are actually circles. They're concentric circles. Okay, they encircle the wire, which is kind of interesting because the magnetic field lines don't start or stop anywhere. They just kind of encircle the wire, centered on the wire. Okay, and we can also find, again using the experiment with the compass or whatever, that if you change the direction of the current, the magnetic field lines actually reverse direction. Okay, now there is a right-hand rule, which we will call right-hand rule number 2, to indicate the direction of the magnetic field along a long, straight, current-carrying wire. So right-hand rule number 1 deals with magnetic force. Right-hand rule number 2 deals with magnetic field. And the way this works is very simple, and you can see it done in this picture. All you do is you imagine grasping the wire with your right hand, with your thumb in the direction of the current. Okay, so in the picture you can see the current is going down in the wire, the person's thumb is pointing down, and notice how their hands wrapping around the wire kind of encircle the wire in a way that indicates the direction of the magnetic field. And so you can see his thumb is pointing down. On top of the wire, his fingers are curling counterclockwise, and so basically the magnetic field is encircling this wire counterclockwise, originating from the wire. Okay, meaning right above the wire, the magnetic field is going to the left. If you were to put a compass, let's say, over here, you would find the magnetic field going down. Obviously, right here, his fingers are going to the left. If he continued to wrap his fingers around the wire, by the time they got to here, they would be pointing to the right, and so on. So they literally just kind of encircle the wire. This is a bad circle, but it's just because I can't draw very well. Okay, so right-hand rule number 2 tells you the direction of a magnetic field due to a long, straight, current-carrying wire. Okay, pause there, make sure you have that in your notes. Okay, and this is basically just pictures showing you the right-hand rule number 2 at work. In this example, in the top left, you can see the current is going to the right. So if you put your thumb pointing to the right, okay, as they curl, notice when your hand is right side up, your fingers are actually pointing towards you if you have your thumb outstretched to the right. If you were to continue to curl them around an imaginary wire, they would actually end up going into the page at the bottom of the wire, and they come out of the page at the top, and that's what's indicated here. And likewise, if the current was going to the left, imagine holding your right hand out in front of you, put your thumb to the left. Your fingers initially go into the page, but if you were to continue to rotate them around, like imagine you're gripping an imaginary wire, if you continue to wrap them around the wire, they would eventually come towards you at the bottom of the wire. And so that's just to indicate in what direction the magnetic field lines encircle the wire. And you can see more examples over here on the right side. Okay, now if you want to be more specific about what the magnetic field lines look like, here is a situation where you have a current carrying wire and the current is going up, and you can check with your right-hand rule number 2 to make sure that these field lines or these magnetic field vectors are drawn correctly. Notice the spacing though, they become more and more spaced out the farther you get from the wire. And so just like with the electric field lines, the spacing has to do with how strong the field is. In other words, based off of this visual, we know that the magnetic field is strongest when you're closest to the wire, and it gets weaker as you go farther away, which It's probably common sense to most people. Anyone who's ever played with magnets knows that, if you have them far enough apart, they don't really affect each other. So distance plays a role. Okay, I want to take a look at an example with this. And I want to see what you think the answer to this question is. So read the question carefully. I don't necessarily expect you to get it right away, although that would be nice. But this is an IB question. See if you can figure this question out. Okay, so let's talk about this question. The question is asking about the direction of the magnetic force on the particle. The particle is out here to the right. Okay, anytime you're dealing with magnetic force, you're dealing with right-hand rule number 1 automatically. That's the only right-hand rule that has anything to do with force. Okay, this particle is moving in the presence of a magnetic field. Now, where is that magnetic field coming from? It's coming from this wire over here. And you might say, wait, doesn't the moving particle, doesn't that create its own magnetic field? Yes, it does, but that magnetic field does not affect itself. Generally speaking, things cannot affect themselves. Okay, so it's like a charge. Stationary charge creates an electric field, but that electric field does not affect the charge that's creating it. Okay, so this charge right here out to the right, yeah, it is creating its own magnetic field, but that has nothing to do with this question. Okay, the only reason it's experiencing a magnetic force is because it is in the presence of some outside magnetic field. Where is that field coming from? It's coming from this wire on the left. Okay, so here we have to employ two right-hand rules. One to find the direction of the field coming from the current carrying wire, and then one to find the direction of the magnetic force. Okay, so the magnetic field coming from the wire, what is its direction? Well, if you put your thumb straight up onto the screen, on the right side of the wire, the field is going into the page. Okay, so I'm going to draw X's to indicate into the page over here. And those field lines would encircle the wire and come out of the page on the left side. Okay, now that we know which way the field is going, we can employ right-hand rule number 1. We put our pointer finger in the direction of the particle's velocity, which in this case is up. Make sure your pointer finger is straight. You have your middle finger, which should point in the direction of the magnetic field, which in this case is going into the page. Your thumb should be pointed straight out. And if you do that correctly, you should find that the force is actually to the left. Okay, so the correct answer is actually A. This question actually is an IB question. It was on the IB exam maybe 5 or 6 years ago, but it's a great concept question. Okay, so pause it there and make sure you understand that concept. Alright, and this is basically just more stuff about the right-hand rule. This question right here is another IB question. Okay, this was actually an older question, maybe from like 10 years ago, but it's still an interesting concept question. So it says the diagram shows two current carrying wires, P and Q, that both lie in the plane of the paper. The arrows show the conventional current direction of the wires. The electromagnetic force on Q is in the same plane as that of the wire. What is the direction of the electromagnetic force acting on Q? Okay, again, anytime you're talking about the electromagnetic, the electric part doesn't matter. Anytime you're talking about magnetic force, you have to use at least right-hand rule number 1. Okay, so that is my hint. See if you can answer this question. Okay, so we're asked about the force on Q. Okay, Q is a current carrying wire. It is moving charge, and moving charge feels a magnetic force only if it's in the presence of a magnetic field. Now, where is the magnetic field coming from? It's coming from P. Okay, so Q feels a force due to the field created by P. Now, what is the direction of the field coming from P? Well, if you employ right-hand rule number 2, put your thumb in the direction of the current P, your finger should go into the page over here on this side of the wire. Okay, and they'd be coming out of the page on the other side of P, that doesn't matter. On the right side of the wire, they're going into the page. So now if you switch back to right-hand rule number 1, you put your pointer finger with the moving charge, which is to the right. You put your middle finger in the direction of the field, which is into the page, and your thumb should point Okay, so the answer there is A. Okay, another great classic IB question. Okay, and so basically, there's an interesting result if you have two parallel wires with a current going in the same direction. Because each one creates its own magnetic field, and each one feels a magnetic force due to the other one's magnetic field, it actually happens that if you have two parallel wires with current in the same direction, they actually attract each other. Okay, so that is just a fun fact. I will try to find a video of that and link it in so you can see it. In fact, that's actually how the ampere is defined. 1 ampere is defined as a current that would cause a force of 2 times 10 to the negative 7 newtons per meter between two long parallel conductors separated by 1 meter in a vacuum. And that was one of the original definitions of the ampere, which is an SI basing it. Don't ask why it's defined with that weird number. That's a different story, but there you go. Okay, see if you can answer this question on your own. Okay, so if you don't just remember the answer to this, you can always just employ a combination of right-hand rule number 1 and right-hand rule number 2. Okay, imagine I1 is creating a magnetic field. If you use right-hand rule number 2, you'll find that on the left side that field is going out of the page, and on the right side that field is going into the page, which means I2 has moving charge in the presence of a magnetic field. If you switch back to right-hand rule number 1, then you should be able to find that, let's see, your pointer finger would be going down, your middle finger would be going into the page, your thumb would be going to the right, which means that I2 is going to feel a force to the right, and I1 is going to feel a force to the left. Okay, that one is, you could also do the same kind of reasoning for I1, or you can think like, Newton's third law, for every force there's an equal and opposite reaction force. However you think about it, you get the result that they actually repel each other. And you can do this demonstration, and again, I will try to find the video of that and link it so you can see. Okay, so let's talk about the very last part of this unit. What happens if you take a long, straight, current-carrying wire and you bend it into a loop? So this would be the field vectors for a straight wire. If you bend it, notice what happens to the field. On the outside of the loop, the field actually gets spread out. It gets weaker. Whereas on the inside of the loop, it actually gets much stronger. It gets concentrated. Okay, the magnetic field inside of the loop is stronger than outside, much stronger. Okay, and so this takes us to right-hand rule number 3. Right-hand rule number 3 has to do with the direction of the magnetic field due to a current-carrying loop. Okay, so number 1 has to do with magnetic force, number 2 has to do with the field due to a straight wire, and number 3 has to do with the field due to a loop of wire. Okay, and it's basically the exact opposite of right-hand rule number 2. You hold your right hand out. Okay, remember this rule number 3 is only for a loop of wire, so imagine your fingers curling in the direction of the current. In that case, your thumb will point in the direction of the field. Okay, so in this case, notice that the current is in a loop going counterclockwise. If you have your right hand out in front of you, make your fingers curl so that they form a loop counterclockwise. Your thumb should be coming out towards your face. Okay, so this magnetic field would be coming out of the page. If you want a better picture, that's what this is right here. Same situation. Current is going counterclockwise. If you use right-hand rule number 3, you see the field inside the loop is coming out of the page. That's why these dots are here. Okay, so that is right-hand rule number 3. Current carrying loop of wire is sent to the right. What is the direction of the magnetic field produced from this loop? Okay, if you make your fingers curl with the current, like it says to do in right-hand rule number 3, if they are curling clockwise, then your thumb should be pointing into the page. And I have a video here that I will link so you can see. Okay, so this is showing you the field due to a straight wire. This is right-hand rule number 2. And this is the field, magnetic field due to a loop of current. That's right-hand rule number 3. Okay, and the very last thing I'm going to mention, besides some application stuff, is what is called a solenoid. Okay, and you might have heard of a solenoid before. Yes, there's a solenoid in your car. It is basically the same principle as what we're going to talk about. A solenoid is basically just a series of loops of a wire. Okay, you can easily make a solenoid by taking like a paper clip and like rolling it around like a nail or a screw or something. Okay, it's just a loop of metal with a current running through it. That's basically all it is. Okay, and so in the last slide we talked about right-hand rule number 3, that gives the field due to one loop. The same right-hand rule works for a solenoid. Okay, you curl your fingers in the direction of the current. Now, why would you want to make a solenoid? Well, we saw a few slides back that if you bend a wire into a loop, the field inside gets concentrated. And it turns out the more loops you have, the stronger the field. Okay, so the solenoid, one of the applications is it gives us a way to make a very strong magnetic field. Kind of like how when we talked about the capacitor, the two parallel metal plates in the last unit gives us a way to make a strong uniform electric field. The magnetic field inside a solenoid is also very strong and uniform. Okay, and so it's very analogous to the parallel plates in the last slide. Okay, same right-hand rule number 3. Okay, you curl your fingers in the direction of the current, your thumb points in the direction of the field. Okay, if you want to draw this into your notes, that might be good. And we don't have time to get into all the cool applications of solenoids. They are used in a wide variety of different fields. I do want to tell you 2 things. The strength of the magnetic field created inside the solenoid depends basically on 2 factors. Okay, number 1, the current. The bigger the current, the stronger the magnetic field. Okay, that's true for a solenoid or any other wire. Okay, the more current you have, the stronger the magnetic field. Okay, number 2, the number of turns of the solenoid. What the heck is a turn? Turn is a fancy physics word for loop. Okay, the more loops you have, the stronger the magnetic field. Okay, and you should know that the magnetic field within a solenoid is relatively uniform. Okay, so I'm just going to quickly go through these slides, and I want to show you some videos having to do with magnetism, and then that's basically it. Okay, if you've ever heard of the northern lights, really quickly, the way the northern lights work is basically the sun puts out a bunch of charged particles, as you can see in this cool little clip, and those charged particles get sucked into the magnetic field of the Earth. Okay, and so because that's what happens with charged particles. Okay, so they get sucked in near the North Pole and the South Pole, and what happens is those charged particles collide with oxygen and nitrogen molecules, and they ionize them. And when those molecules deionize, they emit light. We talked about that in past units about how when atoms or molecules get excited, they emit light. Because electrons fall down in energy levels and emit photons and all that stuff. Okay, and the light looks really spectacular. If you've never seen a video clip of the northern lights, go to YouTube and look up a video of the northern lights. It looks really cool. Okay, it glows all kinds of different colors because there's different atoms and molecules in the air. So just wanted to explain why the northern lights exist. And I am going to attach, or I'm going to link in some videos for you to check out. Not anything super random, mostly stuff just to reinforce the concepts that we've been talking about, because there are a lot of important concepts that you need to understand in this unit. But we are basically done with magnetism. This is the last unit of the semester. Okay, so we are done with 5.4. I would encourage you to make sure you complete your worksheet, read through 5.4 in your textbook, and do the problems in your textbook as well. As always, please let me know if you have any questions, and I will see you guys next semester.